Hi there. In this video, I hope to give you an idea of what exactly we mean when we talk about a reversible process in thermodynamics. So you may have seen it said that all macroscopic processes in nature or reality, they are irreversible. So that's easy to understand if you just think about a car. We know that we put petrol or gasoline in the fuel tank of the car, and then the engine combusts that and it converts that into work. Work is the energy that's required to create or perform some kind of movement. So the car moves along the road, and that is actually work that's done. What doesn't happen is we have a situation where work is done spontaneously and the car rewinds backward in time and reforms the fuel in its engine. So that never ever happens. We know that from our experience in everyday life that such a thing would be ridiculous. But we do have certain situations where this actually can happen if we define it in a certain way. And that's where a reversible process actually comes in. So a reversible process is a theoretical process. It doesn't actually happen in real life the way we have just described it now. But what it is that it's a process that sort of technically undoes the energy transformations that we do on a system. It's a theoretical process that is capable of undoing the energy transformations. So how does it do that? How do we conceptualize such a thing? So the way we think about it is that it happens so slowly and it happens so small, or the change is so small, that the system doesn't change from where it currently is. So we talk about equilibrium states here and thermodynamic equilibrium. So if something is in equilibrium, it's not changing, it's static. There's an initial state where it was, and a final state is what it's become. So if the initial state and the final state, they are the same, it means that it's technically in equilibrium. So we think about a reversible process as being a process where the change is so small and happens so slowly that technically in real life there is very little difference or almost no difference between the initial state and the final state. So when we make a change, it happens very infinitely close to equilibrium. So we can think of a simple example as being this piston that has come up now, and this gas in the piston is being compressed by sand on top of the cylinder. So we can think about a reversible process as removing one grain of sand. If we remove one grain of sand, we adiabatically expand the gas. But think about the position of the piston. The position doesn't move much. So it's at equilibrium, even though we have technically performed a change on the system. So the change that we have done is infinitesimal. So that's the word. And since it is infinitesimal, the system is infinitely close to equilibrium. It's not actually at equilibrium. If there is a change that's being done on it, it's changed from its equilibrium state, but it was done such that it has remained infinitely close to that equilibrium state. So what would be an irreversible process would be to remove a large chunk of sand. Since we have just removed one grain of sand, if we just put that one grain of sand back, there was technically no difference in its, or macroscopically, there was no difference between the initial state and the final state. If we did use a large chunk of sand that we had removed, then that would be a sort of irreversible process. Since the initial state, which is before the one grain of sand was removed, and the final state, after it's been put back, technically the system didn't change much from its equilibrium. It was still infinitely close to its initial state. That's why we think of that as a reversible process. So to summarize, if a system is changing, then it's not in equilibrium. However, a reversible process is an idealized process in which equilibrium is nearly maintained even though the system changes. It's infinitely close to its initial state. So another example of this would be if we think about a scale or a balance. So if you put something on top of one of the sides, we know that it would sink down. So this is a nice way to also understand the difference between a reversible and irreversible process. So let's just say we put a block or some kind of object that weighs something significant on one side of the scale. We know that it sinks down. And since it has moved, we know that there's work done in making that happen. So before it moved and after it moved, there were changes in kinetic energy because it was moving, it had a certain speed, and also there were changes in potential energy because of its changes in actual position. So since there are these conversions between the two sides in terms of kinetic and potential energy, there is another form of energy that is involved in this situation that we have just described. And that is the fact that there is heat being generated at the pivot point. So between the two sides of the scale, there is a rod, and that rod is sitting on top of that pivot. So since it's sinking down one of the sides, it means that this rod is rubbing or moving against the pivot. So that means that there is friction that is being created by that movement. And wherever there is friction, there is heat involved. So the changes in kinetic energy and potential energy are actually being sort of lost, so to speak, by the heat that is now coming out of the pivot point. So that is why it comes to a rest, even if we were to remove that block. So if we do remove that block or that weight, then what happens is we see that the one side goes back to its initial position on the first picture on the left-hand side. So many people are under the misconception that because the system moved back to its initial state, that is a reversible process. But that is not the case. If the weight is removed from the sides, we know that it goes back, or it moves back to rest at its original position. So this act of returning to the original point does not mean that it's a reversible process. It's actually the opposite. Since the sides go back to their original position, it means that it's an irreversible process. So why is it an irreversible process? Well, if we remove the weight, we know that there's changes in kinetic and potential energy. And if there was no heat loss, remember that heat loss is irreversible. And since now this kinetic energy and potential energy is happening, we know that if energy is being conserved, then it would always be changing between kinetic energy and potential energy. But since energy is not conserved, we're losing heat from the pivot because of friction. It means that there is a drain of energy from the system. The kinetic and potential energy that would have been there is now sort of being drained from the system. So if heat loss was reversible, in other words, or if there was no heat loss to begin with, then what it would mean is that the system would just seesaw up and down. There would be no loss of kinetic and potential energy from out of the system in its totality. It means that the sides would just continuously seesaw up and down forever. There would be no drain from the pivot point from heat. So we can now think about this as being a reversible process by, instead of thinking of a large object being put on and removed from the scale or the one side of the scale, we can think of a very small object, and that would be a grain of sand. So if there is a grain of sand on one side of the scale and we remove the grain of sand, well, we can think of the original position, the initial state of the system, as being at rest with the two sides being relatively equal. And after removing the grain of sand, they are still relatively close to the initial state. And you would recall that in the previous illustration that we had used with the sand on top of the cylinder, it's the same or the similar scenario. Macroscopically, we have the two scales at a certain position, and after removing a grain of sand, we have technically performed a change on the system, but we haven't actually changed the thermodynamic states, the macroscopic states of the system. So the initial and the final states remain infinitely close to each other, even though there was this change. So this is how we would conceive of a reversible process. It's a process that results in the system infinitely being close to its initial state. So in reality, if we have differences in pressure and temperature, we can make a process as small as possible by ensuring that we keep these gradients, these changes in these variables, as small as possible. So thank you very much for watching.